Right now, you are watching an AI that teaches itself how to play the game of Pong. Now, it's doing so using an algorithm called NEAT, which stands for Neuro Evolution of Augmented Topologies. Now, in this video, I'm going to explain to you how that algorithm works and then show you how to implement it into this game. Now, although we will be focused on Pong, the techniques and strategies I show you in this video will work for pretty much any game. So if you're interested in building AI and building AI for games in general, then definitely watch through this video and I'm sure that you will learn a lot. Now, I do want to mention that we're not going to code out Pong from scratch like I did in kind of the last video of this where I coded a AI that played Flappy Bird. I'll link that in the description, by the way. What I'm going to do is give you some starting code that has a functioning Pong game, and then we'll look at how we actually implement the NEAT algorithm and move the different paddles and well train an AI. So with that said, let's go ahead and get into the content after a quick word from our sponsor. Before we get started, I need to thank Appify for sponsoring this video. Appify lets you turn any website into an API and can automate anything you do manually in a web browser at scale. With Appify, you can perform web scraping, web automation, web integration, and more. As a developer, you can build your own custom scrapers using the Appify SDK, which is a fully featured Node.js library, or you can use their Python API client. Now, if you do end up making a custom scraper or automation tool, you can monetize your work by publishing your solution to the Appify store and rent your software to earn passive income each month. Now, if you don't want to write a scraper from scratch, you can also fork the code of hundreds of pre-made tools in the Appify store and modify it to your liking. You can get started with Appify today for free by clicking the link in the description and get a $5 credit every single month without even needing a credit card. However, if you do need to upgrade, you can use the code TIM20 for a 20% discount. Thanks again to Appify for sponsoring this video. Now let's get into it. So I want to get right into the code, but I just need to mention that this video here is not designed for complete beginners. So I'm going to assume that you have a solid understanding of Python and that you have some understanding of neural networks. Now, if you don't worry, I will leave some links in the description and some resources to help you. So first of all, if you don't understand Python, or maybe you're just kind of a beginner programmer, you can check out my course. It's called programmingexpert.io. It teaches you fundamental programming concepts mostly in Python. That'll be linked in the description. You can also check out my Neural Networks for Beginners tutorial series. That's free. That's on YouTube if you just want to learn a little bit about neural networks before going through all of the content here. With that said, please do feel free to follow along. You'll most likely be able to get a functioning AI. You may just not understand everything that you're doing. All right, so now that we've talked about that, I will also mention all the code for this video will be linked in the description, as well as all of the documentation and research papers that I reference. Now, I apologize for the long introduction. Let's actually get into the code and let's start creating this AI. All right, so on the right-hand side of my screen here, you can see that I actually have a finished version of this AI. So the right-hand side is the AI, and I'm on the left-hand side. And this is going to be the goal for this video, is to train the AI, watch how it trains, and kind of understand the genetic algorithm, but then be able to actually play against the AI in a game of Pong, or to have two AIs play against each other. So that is the end goal. Just wanted to show that to you. And now what we're going to do is just get into some setup steps here, because as I mentioned, we're not going to be coding out Pong from scratch. What we're going to do is start with an implementation of Pong, and then I'm going to show you how to implement the AI for it. Now, if you do want to code Pong from scratch, I do have an entire tutorial on how to do that, so I'll link that in the description. But for now, I want to get started with the starting code. So what I'm actually going to do is just open up a new folder here in VS Code and then walk through the setup steps with you. So I've just opened up a new folder in VS Code. That's the editor I'm going to use for this video. Feel free to use whatever you want. Now I also have this GitHub link open. This will be in the description, but this is what contains the starting code for this project and the implementation of Pong that we'll use to train the AI with. So go to this link, again, it's in the description, and just copy it if you have Git installed. And if you don't have Git installed, then what you're going to want to do is just click on the download zip here by clicking on code. So code, download zip, and then extract the zip folder and open up that zip folder. But if you do have Git, then you can just copy the URL and you can just clone the repository, which is what I'm going to do. So I'm going to go to VS Code. I have my terminal open, and I'm just going to type in git clone and then paste the URL here. And that's going to give me all of those files inside of this directory. Now I'm just going to start walking you through how this code works. Then we'll build out kind of a basic implementation of the Pong game so we can actually view it and kind of play the game ourselves. Then we'll start getting into writing the AI. So the first thing that we do need to do is actually install a few modules. So if you open up requirements.txt, you'll see that we need neat Python and Pygame. So if you know how to, you can install just this txt file here, or you can just go into your command prompt and type pip install, and then the modules. So the first one is going to be neat Python, and then after that, it's going to be Pygame. Now, I already have them installed, so you're going to see it says requirement already satisfied, but you need both neat Python and Pygame for this video. Now, for some reason that pip command didn't work for you, try the pip3 command. If that didn't work for you, try Python-m pip and then install and then the 2 modules that are listed there. And if that didn't work for you, try Python 3. And if none of those work for you, as always, I'll put 2 videos on the screen that show you how to fix that command. Okay, so now that we have that working, let's just start having a look inside of this Pong folder here, because the Pong folder, it's actually a Python package that contains everything you need to create Pong. So inside of here, we have ball.py. This simply implements the ball. Okay, we have paddle. This is one paddle. We, use 2 paddles in our Pong game. And then we have game.py, which is the class that you're going to be interfacing with. So inside of this file, you can see that we have 2 main classes. We have game information and we have game. Now, the game information class is going to be returned to us, or at least an instance of this class will be returned to us whenever we call the loop method of the game, which I'll talk about in 1 second, but it's just going to give us the game information, right? The number of hits the left paddle has, the right paddle has, and then the score of both the left and the right paddle. And the way the scoring works is that if you get the ball across the other player's side, you get a point. So if I'm the right paddle, I hit it to the left side and they miss, then the right paddle would get a point. Obviously, we want to know all of this information so that we can understand which AI is performing better, and we can train our AI using, this data, right? That's what we want. Then we have the game class. This is the main class that we're going to interface with. And you don't have to understand how the code inside of here works. You just need to understand how you simulate the game using the class, which I'm going to show you exactly how to do. So the first thing we'll do here is initialize an instance. And we do that by passing a window width, and a window height. Okay, pretty straightforward. This is going to be a Pygame window, and then it will handle actually making the game for us. We then have a bunch of private methods, which we don't even have to look at because we're not going to interface with them. And then we have draw. Now, draw is going to actually draw the game for us. You don't have to draw the game. If you don't draw it, you just won't see it. So up to you if you want to draw it or not. And you may not want to draw it because it'll be faster to actually train the AI if you're not constantly drawing it. Then we have move paddle. Pretty easy, but this allows us to move the left or the right paddle. If we pass left true, that means we're moving the left paddle. If we pass left false, we're moving the right paddle. Up true, we're going to move whatever paddle up. Up false, we're going to move it down, right? And then it will make sure that we actually can move it. And it's going to return to us true if we were able to successfully move the paddle, and false otherwise. So if you're trying to move the paddle off the screen, for example, it's going to return false, saying, hey, no, you cannot move there. Okay, continuing, we have loop. This executes a single game loop. So what you need to do here to actually run the game is create your own event loop, which is just going to be a while loop essentially that's running, that's constantly calling this method. And then this method, every frame, is going to return to you the game info, which is going to be the hits for the left and right paddle, and then the score for the left and the right paddle. So at every frame in the game, you will know all of the information, and you can do with it what you want inside of your main game loop. You can decide when to end the game. You can decide if you want to train another AI, if you want to give an AI more points than another one. We'll talk about that later on. Then we have reset. Pretty straightforward. Resets the entire game, okay? That's the game class. That's really all the information you need to know. And one last thing, we have this init.py file, and this just says from.game import game, which means that when I import this Pong, package is what we'll call it, then I'm able to just directly import the game class and start working with it. Okay, continuing, we have config.txt. This is what we're going to use for the configuration for our neat algorithm. Talk about all of this stuff when we actually implement neat. Don't worry about it too much right now. Then we have main.py. This is the finished code. So if you just want to run the AI, like you don't care to go through the tutorial, then you can just run this file, assuming you've installed neat Python and Pygame. But what I'm going to be doing in this video is essentially rewriting this file from scratch so we actually understand all of the stuff inside of here. And then this header comment here is just one of the examples from neat that we kind of reference, or that I've stolen some code from in this file right here. Okay, so that is the gist of this starting code. Not overly complicated. Again, you don't have to understand everything inside of here. Just wanted to give you a brief explanation of what's going on so that when I start writing some code, it makes a bit more sense. So now let's actually implement a basic Pong game. So let's use that game class and just see how we can actually move the paddle up and down and work with those different methods. Then we'll start writing out the AI. So I'm going to create a file here, and I'm going to call this tutorial.py. And inside of here, I'm going to say import. I'm going to import Pygame, and then I'm going to say from, and this is going to be Pong import, and then I'm going to import game. Now I can do this because Pong, which is the folder here, is a package because it has the init.py file inside of it that allows me to directly import anything that it imports. And since it imports game, I get game right here. Now make sure you put your tutorial.py file inside of the neat Pong Python folder and that it's not inside of the Pong folder, okay? Now that we have this, we want to set up a Pygame window. The window is where we're going to draw all of this stuff and what we need to pass to the game class. So I'm going to say window is equal to pygame.display.set_mode. And then inside of here, I have to pass a width and a height for the window. So I'm just going to say width, comma, height is equal to, and then we're going to go 700, 500. Now make sure that whatever the width and the height is that you set, you're going to keep it the same when you're training the AI, because if you change the width and the height, it's going to affect how the AI performs. So just make sure the width and the height you pick right now, you're okay with, and that you're not going to be changing it in, say, the middle of training, because if you were to change, that's going to kind of mess everything up. Just wanted to note that. So we'll pass width and height inside of here. Okay, now that we have a window and a width and a height, we can initialize the game class. So I'm going to say game is equal to game, and I'm going to pass my window, my width, and my height. Now you're about to see how easy it's going to be to run the game. What I can do is create a while loop here. So I can say while true, for example, although I really should just make a variable. So I'll say run equals true, and then while run, and I'm going to say game.loop, and then game.draw, and then I'm going to say pygame.display, where is this here, .update, and this will actually run the Pygame for us. That's literally all we need. Now, I do need some way to quit this while loop. I don't want an infinite loop. So let's implement that, but this is what I was talking about, okay? I'm going to say game.loop. This is just going to constantly run the game loop for me inside of here. I'm saying game.draw, so it's going to draw it, and then I'm updating my display just so I see everything. If I don't update the display, it's not actually going to show that it's being drawn. However, as I said, we need some way to quit. So what I'm going to do is say for event in pygame.event.get, and I'm going to say if event.type is equal to pygame.quit. So that means we hit the red X button on the Pygame window, which you'll see in a second. Then I just want to say run equals false, and I'll just break out of the for loop like that. Okay, and then down here, we can just say pygame.quit, just to make sure the window closes. Okay, that's literally all we need to run the Pong game. And then of course we need a way to move the paddles, but let's run this right now and see if this is working. Okay, so I'm going to bring up, actually I don't need to bring up the console. I can just click run and let's see. And notice that we have the Pong game, and there you go. Now it's going super fast, right? Just because I haven't actually limited how fast the loop is running. I'll show you how we can limit that, but that's how you utilize the Pong game. And then if I want to move the paddle, I would just need to use that paddle move method. For now though, I'll show you how we can limit the speed. So what we can do is create a clock and say pygame.time.clock. And then what I will do is go in here and say clock.tick. And then you pass the maximum number of frames that you want to render per second. So in this case, I'm saying 60. So that means this while loop will be limited to running 60 times per second. That's exactly what tick does for us, okay? So you just put that inside the loop and it's gonna limit the time. Let's run this. And then notice that now we get a ball moving at a reasonable speed, okay? And then it's drawing the score for us. Now, a few other things that we can look at here. When we draw, we have the option to pass two things. Let's just go back here and I'll show you. So looking at draw, we have the option to pass draw score and draw hits. So draw score by default is true, draw hits is false. Pretty straightforward what they're doing, but if I don't want to draw the score, I can pass this false. And if I want to draw the number of hits, I pass that as true. So maybe we'll switch this and just say false and true. And now, rather than it showing us what the score is, it's going to show us the combined number of hits between the two players, okay? So unfortunately, they have not hit the ball yet. Now, one small thing to note here as well is that you'll probably see that when the ball starts in the middle, it's kind of random, the direction that it's going. That's intended, so I have it so it's just randomly coming off at a slight angle so that the AI can't just say sit in the middle of the screen and constantly hit the ball. It needs to actually learn to move towards the ball. That's something I did in the game class that I want to mention. Anyways, see the hits is being tracked up here. That's all good. We now pretty much understand how to use this class. So last thing I'll do is show you how we can move the paddle with the arrow keys, and then we'll start building the AI. So let's do the following. Let's say keys. We want to get all of the keys that the user has pressed. So we're going to say keys is equal to pygame.key.get underscore, and this is going to be pressed. This will give us a list of all of the keys that the user has pressed. So I can just check if they've pressed. In this case, let's go with the W and the S key, and then I can move the paddle accordingly. So I can say if keys And then I'm going to pass pygame.k underscore, and then the key I want to check is W. So that's what I pass. If you want to do A, you would do A, right? If you want to do up, it's actually K underscore up. If you want down, it's in all capitals K underscore down. You can look those up from the Pygame website, but pretty straightforward. And then what I will do is say game.move paddle. Okay. And then what paddle do we want to move? We want to move the left paddle. So let's say left is equal to true. And I want to move up when I'm pressing W. So I'll say up equals true. Okay. And then we can copy this, put this down here. And now we'll say if key is pygame.k underscore s, because, well, that's below W, then we'll say left is true, okay, but up is going to be false. Nice. Now this will allow us to move the left paddle. So let's run the code. And let's see what we get. And notice that if I move S and W, I can now move the left paddle. And if you wanted to, you can implement maybe the up arrow keys for the right paddle. That's as easy as it is, though. And the last thing to look at is that if I do something like game info is equal to this, I can print out, for example, the game info dot, and then let's go left score and the game info dot right score. So the game info class, again, it has left score, left hits, right hits. So we'll use this data to figure out when we want to end the game and how well the players are doing. I just wanted to show you that I can print this out, and let's move the console up and notice we're constantly getting 0, and let's let him score. And then we're going to get 0-1, right? Okay, there you are. Nice. So now that we have done all of that, I want to start building out the AI. So to do that, I want to make a class that's going to have a few different methods. The first method may be something like train AI. The other method may be test AI, right? I need a few different things, and it just makes sense to put all of this in a class. So let's go ahead and do that. So I'm just going to make a class here. Let's do it at the top, and let's say class, I'll call it Pong Game, and then we'll define an init. And in the init, let me just move the mic a bit closer here. We'll take in a window, a width, and a height, and we'll initialize a game. So what I'm going to do is say game here. Let's copy this. Is equal to that, but we'll say self.game is equal to game window width height. So now each Pong Game instance will have its own game. And then inside of here, I just want to grab the ball as well as the left and the right paddle from my game. So if I go to game here, you can see that in the init, we have a left paddle, right paddle, and ball. Now I'm going to want the location of the ball, the location of the left and the right paddle when I'm actually designing the AI. So I'm just going to get those things. I'm going to say self.left paddle is equal to self.game.left paddle. And then self.right paddle is equal to self.game.right paddle. And then self.ball is equal to self.game.ball. Okay. Now that we have all of that, let's make a method, and let's just make this test AI. And for now, we're just going to take in self, and I'm just going to run all of the code that I put right here. Just so that we're not wasting this code, let's put all of it in here. Okay, let's tab all of this forward. And now we have a method that actually lets us test the game. And then later on, we'll make it so that we pass an AI here, and that actually uses the AI to play against us, okay? But there we go, we already have our first method done. Nice. So now that we've done all of that, we need to talk about Neat, because we're going to start actually using Neat to, well, train an AI. And we need to understand how Neat works and what that is. So let me hop over the whiteboard. We'll do a bit of an explanation, then we'll start implementing it. So I'm on the whiteboard, and I'm going to start explaining to you Neat. Now, Neat is Neuro evolution of augmented topologies, and this is what's known as a genetic algorithm. Now, a genetic algorithm takes inspiration from human history and natural selection, and essentially produces multiple generations of what we call genomes. Now, this is a little bit confusing. I'm going to explain this more in depth. But before I get to that, I just want to give you a quick recap on neural networks and how you design a regular neural network, because Neat is kind of an advanced, I don't even know what you would call it, layer on top of neural networks. So when we're designing a neural network, what we want to do is we want to feed some inputs to it, and then we want to get some outputs. Now we need to determine how many inputs we're going to have and how many outputs, and what inputs are going to make sense to feed to the neural network. So when we're talking about our Pong game, let's just draw this out here. We have a left paddle, a right paddle, and a ball. Now there's all different types of inputs that we could feed to a neural network to try to get the paddle to move. But the first thing we should probably determine is, what do we want this neural network to tell us? What is the output going to be? Well, what we want the neural network to tell us is, if we're talking about, say, the left paddle here, is if we should move the paddle up, down, or if we should just keep the paddle in the same location. That's really all we care about. That's what we want to know from the network. So that's what our output's going to be. up, down, or stay still. Now, to try to get the paddle to go up, down, or to stay still, what input should we feed the neural network? Well, it's definitely going to need to know the location of the paddle, right? Now, in Pygame, the location is the top left-hand corner. So in this case, we'll pass, say, the Y of the paddle to the neural network. Now, the reason I won't pass the X is because the X is going to be constant, and you don't want to pass any constant values to a neural network. It's just not necessary to do that. So I don't need to pass the X because, well, it's constant of the paddle. It's not changing. Okay, so we pass the Y of the paddle, and then we want to know the location of the ball, right? That's going to be important. So I'm going to pass the Y of the ball. Okay, so actually, let's not just say P. Let's say Y of ball. And then I'll also pass the distance between the paddle and the ball. Since I'm not going to pass the X of the paddle, I'll pass not just the X of the ball, but I'll pass the distance between so it knows how close we're getting to, right? So I'll just say like this, standing for the distance between the paddle and the ball. Nice. So those will be my 3 inputs to the neural network. So let's clear the screen here. And now let's draw a neural network that's going to have the inputs that we discussed and the outputs. So in a neural network, we have nodes, right? We're going to have our input layer, which I'll draw in red. And this first input, we're going to say is going to be the Y of the paddle. The second input will be the Y of the ball. And then this will be the distance in X between the ball and the paddle. Okay, and then we're going to have an output layer. And for the output layer, since there's 3 possible decisions that we want to make, we're going to have 3 nodes, right? And this first node will say, okay, we want to stay still. This will say go up. And this will say go down. And we'll have to interpret which node kind of represents what. I'll talk about that later on. But the point is we want 3 nodes because we have 3 possible decisions. And so we can say something like whatever node has the highest value is the decision that we're going to take. And then in between here, because this is our input layer and this is our output layer, we're going to have something called a hidden layer or multiple hidden layers. So maybe I have something like 2 nodes in one hidden layer. And then typically what we do is we connect every node from the input layer to the hidden layer. Okay, and then every node from the hidden layer gets connected to every node from the output layer. Now, it's not always the case. Sometimes we're missing connections, or sometimes there's multiple connections. All different types of things can happen, but generally speaking, we have our input layer. We have hidden layers. So in this case, we just have 1. We could have multiple hidden layers. We could have 5 nodes, 10 nodes, as many nodes as we want in the hidden layers. And then we have our output layer. And what we want to do is pass information. It gets sent through the neural network, and then we get some output. And we don't really care how we get the output. We just want to get the most accurate output we possibly can. So that is kind of the brief on neural networks. Again, I'm assuming you understand how neural networks work because I'm not going to explain kind of how the data is getting sent through here. The main thing that I want to show you by looking at this diagram is that it's kind of random or it's kind of arbitrary the way that we're picking the internal architecture of our network, right? Within this box that I'm drawing can really be anything. I don't care what's in the middle of the neural network so long as the output based on my input is valid, right? That's really all I care about. It can kind of just be an invisible black box what's inside of the neural network. And for me to try to determine the number of nodes in each hidden layer, how many hidden layers I should have, that's a pretty difficult thing to do, especially if we're trying to solve a task like training an AI to play a game where this isn't really a well-known task. Well, maybe playing Pong is, but for any kind of general game or maybe a game you've made yourself, there's not a good way to determine how many nodes in our hidden layer we should have, as well as how many layers we should have. We can, try to guess, but it's not going to be very easy to do that. So the reason I keep saying this is because this architecture in the middle is really kind of the question mark. This is what's going to determine really the performance of the neural network, and that's something that's difficult for us to pick. So rather than us deciding it, we're going to get the neat algorithm to do that for us. So let me zoom out a bit here, just so that, okay, I move this up. All right, why is it not letting me zoom out? Okay, you know what? That's fine. We'll just get off the screen. I don't need it to be on the screen anymore. What our neat algorithm is going to do is it's going to create a bunch of neural networks. And these neural networks are going to start with kind of a predefined number of hidden layers, a number of hidden nodes. We'll decide that on our own. And then there'll be some random mutations that are performed to these neural networks. So we'll start with kind of a population here. So let's say a population of however many neural networks we determine. In this case, let's say we start with 10 neural networks. And these neural networks will all be slightly different and have some kind of minor changes made to them from the starting neural network that we define ourselves. So maybe we say that we want to have the network that I said. We want to have 3 input nodes, we want to have 2 hidden nodes, and we want to have 3 output nodes. The number of input nodes and the number of output nodes is always going to stay the same no matter what, but what's going to change is what's in the middle here. The number of hidden nodes, the number of connections, and all of the parameters to the neural network. That's what's going to be modified by the NEAT algorithm. So we start with a population of 10 neural networks, and we're going to call these neural networks genomes, okay? And what we're going to do is we're going to take all of these genomes, we're going to test them, and we're going to determine what their fitness is. Now, the fitness of a genome is essentially its score, it's how well it performs, right? If we're talking about humans and natural selection, which I'm going to get to in a second, it would be how long do you survive, right? Natural selection essentially states that over, tens of thousands of years, multiple generations of humans, the ones that were the smartest, the ones that were able to survive, they bred together. That created a smarter offspring, and then that continued on and on and on. And you'll oftentimes see memes and stuff about, natural selection with the people of today that do very stupid things and end up, potentially dying. Obviously, that's a little bit dark. We don't need to talk about that in here. But the point of natural selection is that over tens of thousands of years, you have a large population of people. They all breed together. They create offspring. The best of those offspring are going to survive. The worst are going to die off. And that means that when you get to, the year 2022, you have a set of humans who are all, to some level, better than the very first generation. Again, depends on the metrics that you're using, but that's what this algorithm is going to attempt to do. So we take every single one of our genomes and we grade them. We give them a fitness. Now, the fitness is how well they perform our task. So in this case, when we're playing Pong, we need to come up with kind of a fitness function and a way to determine what the fitness is of every one of our AIs. Now, I'm simply going to use the number of times that the AI hits the ball. That's going to be my fitness. So if the AI misses the ball, which is going to happen a lot at the very beginning, it's going to get a fitness of 0. But if the AI stays alive for a good amount of time and hits the ball a lot, then it's going to get a high fitness. That's as simple as it is for the fitness function. So we go through, we give them all fitness. Let's just say we have something like 1, 7, 3, 2, 0, 3, 4, 10, 20, 21, whatever the fitness values are. And then what we're going to do is we're going to look at this population of genomes. We're going to keep the best genomes that we have. So maybe we keep like 21, 20, 10. Maybe we keep 7 as well. We're going to discard some of the worst ones, and then we're going to breed the best genomes together and move to the next generation. And when I say breed, what that really involves is looking at the architecture of each of these neural networks, because remember, each genome is really just a neural network, and taking those properties and kind of merging them together in another new neural network. So maybe one neural network has a layer with 2 nodes, the other one has a layer with 3. Maybe we then make a new network that has, 2 hidden layers, one with 2 nodes, one with 3 nodes. Whatever the mutation is, we make some changes and we're kind of breeding the best networks together and hoping to get a better offspring. That's the concept. So we take these, let me zoom out here, and then we move on. This is what we call generation 1, okay? And we move on and we make another generation of genomes that goes here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then same thing with these genomes. We take them, we grade them on their fitness, we keep the best ones, we get rid of the worst ones, and then we mutate the best ones together, create some offspring, and move on to the next generation. And we continue this until eventually we get a genome or a neural network that meets our criteria for fitness. So maybe once the fitness is 500, 700, whatever it is, we say, okay, we're done. We have found an AI that is sufficiently good at the game of Pong. We're going to end the algorithm, and we can then save that AI and use it in our game. Hopefully, this makes a bit of sense. All right, so obviously I am giving a vast simplification to how the NEAT algorithm actually works. People way smarter than me wrote the NEAT algorithm. We're not going to write this algorithm. We're just going to utilize it. That's why we have the config file and we installed that module. And NEAT does a lot more than what I'm explaining here. It actually will keep different species of neural networks. So what I mean by that is we'll group maybe, like let's say these, and these together into 3 separate species. And we'll try to make sure that through our different mutations, we're keeping at least 1 or 2 genomes from each species so that we don't have a species go extinct, right? And the reason we would do that is because there may be a species that's not very good right now, but may have a promising architecture for later on. Now, there's all kinds of other considerations like that, like how long do you keep a genome that's not performing well? If I have a species and I have 1 genome in there and it's not performing well for, say, 10 generations, is that sufficient for me to say, okay, I'm going to get rid of it? I don't know, all kinds of questions like that. Now, there's also the ability to add random mutations to offspring and kind of children of other genomes. So what may happen is you may take the best genome, and rather than breeding it with another one, you may just add a random mutation. And a mutation may be disabling a connection, or adding another node, or slightly changing the weights and biases of the neural network. There's all kinds of stuff that can go on, and that's why it requires a lot of generations typically to train an artificial intelligence. So we're going to start with a population of close to 50 genomes. And then what we're going to do is run them through about 50 generations until we reach a genome or a neural network that plays the game of Pong decently well. Okay, so that's it for the explanation on NEAT. Hopefully that made a bit of sense. Now let's hop over to the computer. We'll start actually implementing this, which won't take us too long. And then we'll talk about the different strategies on actually testing the fitness. Because as you're going to notice here, the fitness is the most important part. We're going to keep the best, get rid of the worst, generally speaking. And so we really need to make sure that we're judging these genomes properly and that we know which ones are the best by giving them the most accurate fitness. Okay, with that said, let's hop over to the computer. So I'm back on the computer, and I just want to spend a second telling you about some resources. So first of all, this is the NEAT paper. This explains NEAT, gives an overview of it, some of the pros and cons, and it's obviously going to be a way better explanation of how the algorithm works than what I could have just given you. So please do have a read of this. It's not super difficult to read. It's only 6 pages long, and it will really crystallize probably a lot of the questions, or I guess just your understanding of the NEAT algorithm. Anyways, that's the resources. That's in the description. And then continuing here, I have this example from the NEAT documentation. So NEAT Python documentation. This is one of the examples they provide, and it talks about the fitness function, running NEAT, getting the results. I'm not going to read this to you. You can feel free to read it on your own. And then there's some example code. A lot of the code we have is straight from here, as well as a configuration file. So this is the default configuration file for the example they're using, which is the XOR example. Again, read this if you want to learn more about it. But the configuration file that I have in the project that's already written for us is essentially the exact same as this, with just a few minor changes. So I will talk about what I've changed, but if you want to understand what every single one of these like 70 lines means, you can click on configuration file description, and it shows you fitness criteria and fitness threshold, like all of the different sections in this configuration file. It talks about how you use them and what you can set them to. So again, I'm not going to spend the time reading this all out to you. That's kind of what you can do on your own time. You do not need to go in and touch anything if you don't want to, but I know some of you are going to ask, what does this do? What does that do? If that's the case, please go here and read this. It gives you really good explanations. Okay, so now we're back here, and we need to start working in this configuration file and understand a few of these important aspects so then we can use it for our NEAT algorithm. So let's start going through this file here. These are going to be the 3 most important things you want to have a look at, so just pay attention here. Fitness criterion is telling us when we reach the fitness threshold, essentially. So it's kind of confusing the way I explain this, but the fitness threshold is when we're going to stop the algorithm. And if this is max, that means that once we hit this value for at least one genome, so once a single genome has a fitness of 400 or more, then we're going to stop. That's what max means. Now, if I make this mean, that means once I have all of my genomes having an average fitness of 400, I'm going to stop. And if I make this min, that means once the minimum of any genome that I have has a fitness of 400, then I stop. So I want this to be max. Again, once I find a single genome having a fitness at or above 400, we stop the algorithm, and then we would return that genome, and that would be our kind of AI, right? Then population size, that's what pop size stands for. This is how many we want in our population. I'm going to go with 50. And the way we're going to test this is that if you increase this, it's going to exponentially increase how long it takes to run. So already training this AI could take, 20 minutes, an hour, could take a good amount of time depending on how long you run it for. So if you make this larger, it's going to take significantly longer. So I'd recommend you keep it at around 50, but you can mess around with higher or lower values. I won't make a massive difference to the performance, but the speed, yes, it will. So I think 50 is like a good minimum to keep it at. Some of you may want to do it at like 100 or 150. But for now, just go with 50. And by the way, everything in this file, please feel free to change it. A lot of this is just the default that I took right from the NEAT website, and I've just modified a few things. So continuing, I'm not going to explain a lot of these. Again, you can read the documentation to see that. But I want to go to default genome. Now, the default genome, we do need to modify a few things here because we need to say set the number of input layers and output layers and all of that kind of stuff. And we also changed the activation function. So I'm not going to necessarily explain what the activation function is, but essentially what it does is it takes the result from a specific node and it just converts it to a different value. So I run the result from a node through the activation function, then I pass that value to the next node, and this makes it so that our values are going to be within a specific range. In this case, I've changed the activation function from the default of sigmoid to relu, which is rectify linear unit. And this function, actually, I have a photo of it right here. I'll just pull it up. This is the relu function. Okay, of course. You can see it on the right-hand side of my screen. It just makes it so the minimum value we possibly have is 0, okay? That's relu. Sigmoid is a different function. So I've changed these to relu. That's the only change I've made there. Here, have not made any changes. There's all these other things like, okay, what's the probability that we add a node or delete a node or all that? And continuing, where we really want to look at is, where was it? Right here. Okay, network parameters. This is what we care about for right now. So we need to make sure we change these, and they will already be changed for you, so that the number of inputs is 3 and the number of outputs is 3. Now, the number of hidden is the number of hidden layers you want to start with by default. In this case, I'm going with 2. However, you could change this to 1, 3, whatever, 0. Again, it's kind of a random value that I've picked, and this will change over time as the mutations are applied to the neural network. So just go with 3, 3. You can mess with this, make it 1, make it 2, make it 3, whatever. I'm just going to make it 2 for now. Okay, so last thing to explain in this configuration file, feed forward. Make sure this is true. Again, it will be true for you, but I've changed this from false to true. Now, what this means is that we're just going to get a regular neural network where we feed inputs and we get an output. If you make this false, you get something called a recurrent neural network, which means the output of the previous call to the neural network is going to be an input to the next call. And that is so you can kind of save information. You can save like the history of the neural network, if that makes sense. We don't care about that here. And if you do that, you're going to get some weird results. So just make this true. And then initial connection, full direct. What this means is that we have directed connections between every single node. So we have a fully connected nodes. Every node in the input layer is connected to every node in the hidden layer, every node in the hidden layer, every node in the output layer. Okay. All right. So now let's actually use the configuration file. So to do that, I'm going to say import neat. And then I'm also going to import OS just because we need to find the path to the configuration file to load it. Then I'm going to come down here. I'm going to say if __ name is equal to __ main, just making sure that we ran this file, not that we imported it. I am going to load the configuration file. So I'm going to say that my local directory is equal to os.path.dir name, and then __ file __ with a lowercase. This is a special variable, just gives you the current file. I can get the directory name of it. And then what I'm going to do is say that the config path is equal to os.path.join. And I'm going to join the local directory with config.txt, okay, which is what we have right there. Now, if you change the name of this, you're going to have to change that, but I assume most of you are working with the starting code. Now that we have that, we're going to say config is equal to neat.config. And actually, let me just copy this in because it's going to be a bit easier than typing all this out. Okay. And then we're going to say neat.default genome, neat.default reproduction, neat.default species set, neat.default stagnation, and then the configuration path. Not going to explain this too much. Essentially, we're just passing the different properties from the configuration file that we want to use. And I mean, you can read this if you want, but these are the ones that we want to use, right? Default genome, default reproduction, default species set, default stagnation. And so I need to make sure all of those are in my configuration file, and they are. And then lastly, I pass my configuration path. So now I've loaded the configuration file. Now we need the configuration file to actually create a neural network. So that's what we had to load it, okay? Now that we've loaded it, what I want to do is I want to run the neat algorithm. So I'm going to make a function and say define run neat, okay? And this is just going to take in the config. Okay, so here we can go, say run neat, and we can pass the config. Now inside of run neat, I need to create kind of my neat runner. I don't even know what you would necessarily call this, I guess my neat population. So I'm going to say p is equal to neat dot population. And for the population, I'm just going to pass the config, okay? So I'm initializing a population of genomes using the configuration file. Now that I've done that, I'm going to add a few things to this that makes it so we get some output to our screen. Now, all of this code, again, is coming really right from the Neat website, so you can reference it there as well. But I'm just going to say p.addReporter, and I'm going to say neat.stdoutReporter, and then I'm going to pass true here. Now, this just means we're going to report data to the standard output, so we'll actually see what generation we're on, the best fitness, the average fitness, all that kind of stuff. I'm then going to say stats is equal to neat dot, and then this will be statistics reporter. So let's write it like that. Inside of here, we don't have to pass anything, and then I'm going to say p dot add reporter stats, and then finally p dot add reporter, and I'm going to add neat dot check pointer 1. Now, this is really important that you do this. The check pointer is going to actually save a checkpoint after every X generations, X being the number I passed here. So I'm going to save one after every 1 generation. Now, what this allows you to do is restart the algorithm from a checkpoint. Now, you want this because it could take an hour, 2 hours, a day, 2 days to run this, depending on what you have in the config file. So obviously you want to save your progress and be able to kind of restart and maybe train differently from a certain point in time. So that's why we're checkpointing at every 1. You may want to checkpoint at every 5 generations, whatever. And to actually load from a checkpoint, let me just copy this in. What you would do is you would comment out this line, and you would just put the name of the checkpoint that you want to load from, okay? Pretty straightforward. Neat.checkpointer.restore checkpoint, and then whatever the number is, you'll see them being saved as we run this. And then that's instead of the population. But of course, we don't have a checkpoint, so we're not going to do that right now. All right, so now that I've done this, I'm going to say p.run. I'm going to pass a function, which I've yet to write, called eval genomes. Then I'm going to pass the number of generations that I want to run this for at most. Now, you can read what it's saying here. We're passing what's called the fitness function. The fitness function is going to take all of my genomes, which are in the current population based on whatever generation it is, and it's going to give them a fitness. And then based on what their fitness is, once that function is finished executing, then the neat algorithm is going to perform its mutations, and then it's going to go to the next generation and get the fitness for them. So what I'm going to do is say define eval underscore genomes, and I'm going to take inside of here my genomes, which are the neural networks in the current population, as well as my configuration file. Okay, so let's just quickly talk about what we did. We set up our population using the configuration file. Then we added the reporters and the check pointer just so we see some data on the screen, and we're checkpointing at every 1 generation. Then we're saying p.run. We're passing the function. Make sure you don't call the function. Just pass the name of the function. It will automatically pass this data for us. And then the maximum number of generations we want to run for, which is 50. Now I can actually say winner is equal to p.run. And this will give me the best neural network, or the one that hits the fitness threshold while running this. So either we'll get to 50 generations, and then whatever one has the best fitness will be the winner. Or if we hit one that, or if we get one, sorry, that has 400 fitness or more, it will be returned to us at whatever generation that occurs. Okay, now we have eval genomes. Now, inside of here, what we need to do is we need to set a fitness for every one of our genomes. And to do that, we need to run them through the Pong game. All right, so let me take a quick pause here and explain the thought process behind how we're going to train this AI, because it's a little bit complicated, but it is necessary to avoid getting kind of stagnation in training. So there's a lot of ways that we could train a Pong AI. And the whole issue here is that this is a multiplayer game. If this was a single player game, no problem. It'd be really easy to train because the environment's always the same, right? It's always the same single player environment, so everything's consistent and we get a really fair fitness reading. However, in Pong, the performance of our player, our AI, depends on the performance of its opponent. And so we need to find a fair way to train all of our AIs by either playing them against, say, the same opponent, or maybe each AI against every other AI. There's a lot of different possible ways to go about doing this. So the first approach you may think of is, okay, well, let's train the AI against the same opponent every single time. If we do that, then we get a consistent fitness score. That's correct, but the issue is if we train against the same opponent, we need to have an opponent that's as good as can possibly be, right? Because if we have an opponent that's really bad, we're going to get a false sense that our AI is good, so we need an opponent that's as good as possible to really determine the fitness of our AI. But the whole point of making the AI is to find a really good AI at playing Pong, so we don't have that available, right? Unless we were to hard code something out, which is definitely possible. You could hard code this without actually making, the neat AI for it, but this is, much neater, much cooler. So we're going to eliminate that approach because it doesn't make sense for us to kind of hard code out an opponent to play against the AI. So the next approach is let's train the AI against itself. Now, this is a reasonable approach to do this, but what's going to happen if you train the AI against itself is that even though you're going to get a very fair fitness reading, the AI is going to learn how to play only against itself. it's not going to learn how to play against an opponent that makes seemingly random moves. And if it's only learning how to play against itself, even though it may look like it's going to be very good, we have no idea what's going to happen if we put it against an opponent where it can't predict what the move of that opponent is going to be. So we can't really go with that approach. I mean, we can try that, but we're probably going to end up with AIs that are really good against themselves and look amazing, but then when they start playing against me or you, they have no idea what to do. So the last approach is we need to train each AI against each other. So either I take pairs of AIs, so maybe like AI1 and AI2, and train them against each other and then get their fitness, or I take each AI and I train against every single other AI and take kind of a sum of the fitness of all of those games. Now, that's the approach that we're going to go with. And the reason we're going with that approach is because, again, how good your AI is or how good the fitness is dependent on its opponent. So to make everything as fair as possible, we want each AI to play against every other AI. Now, that is going to take a long time, but it's going to give us the most accurate fitness and actually end up being one of the quicker training routes. So that's what I'm about to implement. Apologize for all this talking, but again, you got to understand the theory behind what we're doing and some of the potential problems that come up in a multiplayer game. So let's try this now. I'm going to, again, be kind of looking at my screen. I don't have all this code memorized. So if you see me looking over here, that's what I'm doing. I'm just referencing my code. So the first thing I'm going to do is say width height is equal to 700, 500, because we need to set up a Pygame window so we can pass it to this game instance or to the Pong game instance where I'm actually going to write a method that will train the AI for us in kind of a similar way to how we were testing it. So I'm going to say width height, and then I'm going to say window is equal to pygame.display.window or .set underscore mode, and then width height. Okay. And now that we passed width height, what we can do is say for I, comma, and then I'm going to say genome underscore ID, genome, I think this is correct, in, and this is going to be enumerate genomes. Now let's go genome ID 1 and genome. So first thing to understand here is that genomes is going to be a list of tuples where each tuple has the genome ID as well as the actual genome object. Now remember, I want each, genome to play against every other genome. And so the reason I'm enumerating here is so that I can make sure we're not repeating games, which you're going to see in a second. So I'm going to say for, and then this is going to be genome 2 or genome ID 2. Genome 2 in, and then this will be genomes at I+1 colon. Now I spelled genome wrong. And then colon, and then for now we're going to pass. So this is kind of the setup of our for loop here. We're saying for I, which is the index of all of these genomes, genome ID 1, genome 1 in enumerate genomes, and then we're saying for genome ID 2, genome 2 in genomes I+1 colon. Now the reason we need I+1 colon is to make sure the same genomes don't play against each other multiple times. They would be swapping on the left and right hand side, but to avoid doing so many operations and to cut it by a significant amount, I'm going to make this I+1 just so that the same genome doesn't play against each other multiple times. Now the issue with I+1 is that eventually we're going to get I being equal to the last index. And then when I add 1 to it, we're going to get an index out of range error. So I'm just going to say if I is equal to the len of genomes minus 1, then break, just so that we end. Okay. Hopefully that makes sense. That just avoids having the index out of bounds error here. Okay. So now inside of here, what I want to do is I want to create a game and I want to test the two genomes against each other. So I'm going to say game is equal to Pong game, and I'm going to pass my window, my width, and my height. Now, before I do that, if I can type properly here, I'm just going to set up here, I'm going to say genome1 dot fitness is equal to 0. Now, these genomes do not have a fitness attribute on them by default. So the reason I'm doing this is so that later on I can add or subtract from the fitness as opposed to setting it, because I'm going to be adding and subtracting to it multiple times. Again, this will all make sense when I write more code, but I'm saying genome1.fitness equals 0. And then down here in this next for loop, I'm going to say genome2.fitness is equal to 0 if genome2.fitness equals none, else this is going to be genome2.fitness. Now, this is an inline if statement. And the reason I'm writing this is because for my genome2, I need to set its fitness equal to 0 when I first pick up this genome when this is the first genome that I'm having a look at. Now, the issue is that I don't want to set its fitness to 0 if the genome already has a fitness value from being ran multiple times. So if we're looking at this, I have genome 1, right? And then this for loop is going to run every time that this for loop runs. So on the next iteration of this for loop kind of restarts, and I'm going to be looking at the same genome multiple times as the opponent to this genome. So I don't want to set this genome's fitness equal to 0 if it already has a fitness value, but if it doesn't have a fitness value, then I need to initialize its value, and so that's why I'm writing this here. Hopefully that's all good. And just to make sure, I think this will be fine because this genome will only ever be encountered in this for loop. Yeah, we should be good with that. Okay. So now that we've set the fitness values, we initialize our Pong game. So game is equal to Pong game. And then what I'm going to do is I'm going to train my AI. So I'm just going to say game.train_AI. And I need to pass to this genome 1, genome 2, and then the configuration file. Okay, that's all we'll pass for right now. And then I'm going to write this method on the game class, and this game class will set the fitness for us. Okay, so this is almost all we need in here. We'll make a few slight changes, but we're just going to train the AI. So we pass genome 1, genome 2, and then it will simulate the game between the two AIs and set their fitness. So now we're going to go up here and let's just write it from scratch. I don't want to copy this. I'm going to say define train AI. And inside of here, I'm going to take genome 1, genome 2, config, and then I need to make sure I have self as well. Okay, so self, genome 1, genome 2, and config. And then I need to run both of these genomes, right? And I need to pass my input to the neural networks, get the output, analyze the output, and then make a move for my paddles. So similar to what I've done up here, I'm going to say run is equal to true. I'm going to say while run. And then I'm going to say game, so self.game.loop, self.game.draw, and then pygame.display.update. Okay, so now that we have this game loop set up, similar to what I did here, I'm just going to take this event loop, and I'm going to say, let's get into the right method here. For event in pygame.event.get, I just need a way to quit, right? So I'm putting this in here just so I have a way to quit. I'm going to say run equals false, but I'm actually, you know what? I'm not going to say run equals false. I'm just going to return false here. And the reason I'm going to return false is because what's going to happen is we're going to constantly call from eval genomes this game, right? I'm going to constantly be creating a new game and constantly running it. And so what happens is if I return false here, then that's fine. I end the current training, but then I'm going to train again and again and again. And I want when you click the X button to just completely exit the program. So I'm going to say force_quit is equal to this. And actually I'll say if force quit, then quit, okay? And in fact, I don't even know why I'm doing all this. This seems a bit too complicated. Let's just do this. Let's go here and let's just say quit. So if you hit this, we just quit the entire program. Quit just completely ends the game, okay? Say quit, that's just going to end the program for us. So I can avoid having to return values back and do all of that stuff. Okay, so now we have a way to exit. We're looping, we're drawing, we're updating the display. And what else do we need to do here? Well, let's have a look at the game information. So let's say game info is equal to self.game.loop. And now that we've done that, we need a way to actually move the two paddles using genome 1 and using genome 2. Now, what we can do is we can create neural networks for both of these genomes, then pass inputs and get the output. So I'm going to do that here. I'm going to say net1 is equal to self. Actually, it's not going to be self. It's going to be neat.nn.feedforwardnetwork.create. I'm going to pass my genome and the configuration file. Okay, so that's net1. And then net2 is going to be the same, but it's going to be with genome 2. Now, to use the networks, what we need to do is say, and we'll do this before we call the game info, we're going to say net1.activate, and we're going to pass the inputs to the network. So the inputs that we want is we want the y coordinate of the paddle, we want the y coordinate of the ball, and we want the distance in the x between the ball and the paddle. Now, it doesn't matter the order that we pass them in, so long as we pass them consistently in the same order. So let's say output. Let's go output 1 is equal to this, and we'll pass self.left paddle dot y. It has a y attribute on it. You can look at the paddle class if you want to see that. Then self dot ball dot y. And again, remember, we have these up here, so that's how I'm accessing them. And then we want the absolute value of the self dot left paddle dot x minus the ball dot x, okay? So this is always going to be positive. Nice. So that's what we have for output 1. And then we want output 2. So output 2 is going to be equal to this, but it's going to be net 2. And rather than left paddle, it's going to be the right paddle. Okay, and then that's ball.y, and that is the right paddle. Nice. Okay, I think that's all good. So this is going to give us an output. Now, the output is just going to be the numeric values associated with the 3 output nodes in our neural network. So we need to actually interpret that, and we need to select the maximum value from those outputs. Now, since I understand it's a little bit confusing, let's just print them out for now and just have a look at what's happening. So let's go output 1, output 2. Now, I also need some way to end the game here because I'm not ending the game in this game class. I'm relying on whoever's using the game class to end it based on this info. So I'm just going to put in a statement here, and I'll do this at the bottom. I'll say if, and this is going to be game info dot left score is greater than or equal to 1, or game info dot right score is greater than or equal to 1. Then I'm just going to break. But before I break, I need to set the fitness of my 2 genomes. Now I'm going to say, actually, it won't be self. It's just going to be, let's say genome 1. Okay, instead of doing that, let's go define, and this will be calculate fitness, and we'll take in self genome 1, genome 2. Sorry, I was just contemplating how I want to do this, but I want to do it in a method. So I'm going to say self dot, and then this will be calculate fitness, and we'll pass genome 1 and genome 2. And actually, we will pass the game info as well. I guess we need that data in here. So pass game info. And then inside of here, we'll deal with what the fitness calculation should be. Okay, so there's a lot going on here. Believe it or not, we're actually almost done. We just need to move the paddles. But I want to kind of take a pause, explain what I've done so far, just so I'm not confusing you guys too badly. Then we'll run the code, see what we're getting right now, and then continue from there. So let's go right to the beginning. We have our local directory, configuration path. We essentially read the configuration file, and then we pass that to our run neat function. We set up our population, all of our reporters and all of that. And then we run the eval genomes function up to 50 times. Okay, so we come here, we set up a Pygame window because we need that for our game. And then we say for I, genome ID 1, genome 1. We actually don't care about the genome IDs, but we'll just leave them there in enumerate genomes. And what this whole set of for loop is going to do here is it's going to run each genome here, so each genome 1, against every other genome exactly 1 time. And then the fitness for that is going to be the sum of whatever the fitnesses they get for every game. Okay, then we set the fitness because we need to initialize an attribute. We then go and loop through all of the other genomes, set the fitness if they don't already have one set, and then we train the AI, okay? Genome 1, genome 2, config. Coming up here, we set up our 2 neural networks based on our genomes. We then run the game. Okay, we have an event that just allows us to actually quit, and then we get the output from both of our neural networks. Now we're going to use this output to move the paddles. We're going to do that later. We run the game loop, which now that I'm thinking about it, I guess we can run the game loop here. That's fine. And then we have self.game.draw. So we just draw the game and then we update the display. And then here what I've done, I didn't really explain this. I'm essentially saying that if either paddle misses the ball once, we're immediately going to end the game. Now, the reason I'm doing this is because if the paddle misses the ball, I don't want to keep running it like multiple times, 50 times, 100 times, whatever, because it's most likely going to miss almost every ball. I want to be in a situation where as soon as it misses, we just immediately move on to the next paddle. And that way it doesn't get any higher fitness score. And I just kind of stop testing that one because it could take a long time just for it to continue to miss balls. Again, I know it might be a little bit confusing, but the score is telling me again how many times the ball has gone off the opposite person's side. So if the left score is 1 or the right score is 1, that means either the left or the right paddle missed the ball. And since they missed the ball, then we're just going to stop, calculate the fitness, and then move on. Now, the only issue with doing this here is that what's going to happen is that as soon as even your opponent misses the ball, you're going to stop as well. We're going to stop calculating your fitness as soon as you or your opponent misses the ball. Now, this is a way for me to quickly train, because if I don't do that, again, it's going to take way, way longer to train, like significantly longer. So you could come up with other approaches and other fitness calculations, but this has worked for me this far. That's why I'm doing this. Again, feel free to change this as you please. And then if that happens, we're going to end. So we're going to calculate the fitness and then break out of this loop and then kind of move on with life. All right. Okay, so let's run this so far. Let's just see if this is working. You're not going to see kind of anything moving on the screen really, because we're not actually moving the paddles, but you will see in the console what our outputs are, and you'll see what the neat output is as well. So let's close CMD, let's run this, and let's see what we get. Okay, it says name ball is not defined. Self.ball.y. Oh, I just put ball.x. Sorry, guys. Let's make that fix. So this is now self.ball, and this is self as well. Let me scroll over so you can see, okay? Nice. Okay, so let's clear and run and see what we get now. And there we go. Okay, so we can see that we're getting a bunch of results. Let me close this. We're getting a bunch of results here. And what we're going to do is we're just going to take whatever the maximum value is of all of these things, right? So we'll treat the first column as staying still, the second column or the second index as moving up, and then the next one as moving down. And as you can see, right, we're getting, sometimes we're getting a bunch of different values. Sometimes we're just getting 0, and these values will start to make more sense as the AI trains itself and gets better. So to do that, we're going to say, let's go here, result 1, or we'll say decision 1 is equal to, and then this is going to be the maximum of output 1. Well, we're going to index this. So I'm going to say output 1 dot index the max of output 1. This is going to give us the index, so either 0, 1, or 2, and we'll say 0 is stay still, 1 is move up, and 2 is move down. Hopefully that makes sense. We're just getting the index of wherever the maximum value occurs from output 1, and then we'll say output 2 is equal to output 2 dot index the max of output 2. So now that we know, sorry, not output 2, decision 2. So now that we know the decision, we can then write some if statements that say, okay, if this is the decision, move here. If this is the decision, move here. So I can say if decision 1 is equal to 0, then we just don't do anything, right? Because we're staying still. I can say elif decision is equal to 1. Then we will say self.game.move paddle. And we're going to say left equals true, because the net 1 is going to be our left paddle. And then up equals true. Okay, and then else, we'll say self.game.move paddle, left is equal to true, and up is equal to false, because that's moving down. And then we'll just copy the exact same thing and just tweak it a little bit. So now this is going to be decision 2, and then we just need to change left to be false, because now this is the right paddle. Okay. So that's how we'll move the paddles. And with that, we've actually set up almost all the training for the AI other than the calculate fitness function, which we'll do in a second. But now, if I clear this and rerun, you should see that the paddles move, right? Now, they're not really doing very well for us, but they are moving. And yeah, there you go. So now the paddles are actually moving based on the neural network. And once we start implementing the fitness and the different generations, then you'll see that they'll slowly start to get better. So let's close that. I also want to change something here where it says draw. So for the draw, I'm going to say draw score is equal to false. Instead, I want to draw the number of hits they have. So I want to say draw hits is equal to true. And just to show you that change, let's run it. And notice that now we just get this red thing being drawn that's telling us the number of combined hits between the left and the right paddle. Okay, so now that we've done that, all we need to do is implement the fitness. Once the fitness is implemented, we're pretty much done with the code, and we just need to wait for it to train, and then I'll show you how to save the best, run, test it, all that stuff. So to do this, we're simply going to say genome1 is equal to, dot fitness is plus equal to, this is going to be game info dot left hits, like that. And then I'm going to say genome2 dot fitness plus equals game info dot right hits. So that's actually all we need for the fitness. Again, we'll just add how many hits they had in the game. And we're adding, not setting. If you set, that's no good. That means only the last game they play is going to account for their fitness. We care about every game they're playing because we're playing against every single AI. Now, the only thing that we want to implement here is we want some way to essentially end a game when the hits get too large, because you'll get to a point where you do have two perfect AIs, and when they're playing against each other, they can play infinitely. So we just want to make sure that the number of hits between them doesn't grow so large that we play too much, right? And that biases our score. So let's say, and game info dot, let's just go with left hits is greater than 50. And sorry, not and, we're going to say or. So essentially what this is saying is that if the player on the left gets 50 hits or more, or gets more than 50 hits, then we're just going to stop, because they'll still get a very high fitness score, but we don't want them to play infinitely, right? Again, that's just going to make the training really long, and that will actually give us an infinite loop. Now, the reason why I'm not checking the right hits is because the right hits will always be either one more or one less than the left hits. So there's no reason for me to check the right hits as well. If the left hits is greater than 50, then the right hits will either be 50 or it will be 51 or it will be 49 or something like that, right? It's very similar, so it doesn't really matter. And the reason why that will be the case is because when the ball starts on the screen, it will randomly start either on the left or the right-hand side. I don't know where it's going to start, randomly left or right. Yeah, hopefully that makes sense, but that's why we're checking that. Okay, so now that we've done that, let's run this. Let's just see how it works for a generation or two, and then I'll show you how we tested and how we saved the best AI. Okay, so let's go ahead and run the code. All right, so I've just let this run for a few generations, and I'll just talk to you about some of the data we're getting here. Then we'll kind of look at the AI, see how it's doing now on, I guess, generation 4, and how we can actually test the AI as well. So we have the average fitness of 4.0, actually not bad for the first generation. That means at least some AIs were hitting the ball, right? We have best fitness of 20. That means one AI through all of the different games that it played hit the ball a total of 20 times. So it played 49 games and it would have missed the ball, 29 times and hit the ball 20 times. So not great, but for the first generation, we can live with that, right? Then we have average adjusted fitness, 0.347. Mean genetic distance. This is the, I guess, difference between the neural network architectures. Kind of hard to explain exactly what the magnitude means here, but the larger the number, the more different the different neural networks are that you have. Then you have the population of 50 members in 2 different species. So species with ID 1 is here, species with ID 2 is here. Tells you how long the species have existed. And then the size. There's 19 in species 1, 31 in species 2, and then we have a fitness of 20 and a fitness of 10. Now, that's the best fitness in this species and the best fitness in this species. And then the adjusted fitness for that species, okay? Coming here, we have now 19 in species 1, 31 in species 2. Fitnesses have now changed, and the stag here is telling you the stagnation of the species. So how long has it been stagnant for? Continuing, we now come here, and now the reason this is getting a 1 for stagnation is because its fitness score is less than it was last time. So it's now being stagnant, right, based on the mutations that would have been done. And you see that we've actually now moved some of these neural networks into the other species based on the architecture of the internal neural network, okay? And continuing, we come here, we're seeing the fitness is increasing. The average fitness goes up, best fitness 68. And you will notice that sometimes you will go down. So you'll hit a generation where your fitness will drop drastically. That's fine. That does happen. And again, that's because we're adding random mutations. We're doing changes. And it's not always guaranteed to give us a better neural network. We just hope it's going to do that. Now here we're at a stagnation of 3. In the config file, I believe we had 20 as the extinct stagnation. So once that hits 20, if there's more than 2 species, then it will actually make the species go extinct because it's not been improving over a period of time, right? So all this different kind of stuff, lots to learn, lots to look at. I'm by no means a pro here, but I have figured out how to make a few AIs using Neat. And so obviously the tutorial. Now this is running, and you'll notice that we're going to get a lot of low scores, right? But once in a while, you will see kind of a decent rally. And it's difficult to really tell how well you're doing based on just watching this, because you only need one AI to perform well to really get a good AI, right? To get a good result out of this. And that AI will play against every other AI. And since all of the other AIs are going to be really bad, what's going to happen is that this AI will hit the ball every time, but then it will never be returned. And so it will look like the rallies are always short, but that's just because the opponent of the really good AI can't return the ball, right? So there's all kinds of stuff like that to think about. And this took me a few days of kind of messing around with to really understand. So this is running. We'll leave it running for now. And while it's running, let's just work on actually how we would test the AI and a change or two that we could make here. And then what you can do is you can stop it. We can rerun the code and then we can return from the checkpoint that we were just at so that we don't have to redo all of the training that we already did, right? Because you're going to notice this takes a long time. Like the average generation, I think, is about 2 or 3 minutes long. Okay, so if we want to train the AI, test the AI, not train it, we have test AI. And what we're going to take in here is a genome, which will just be the best AI, right? And then from the genome, we will create a neural network, and then we'll use the neural network to move the AI. So we're just going to say net is equal to, and then actually we'll need the config as well. So we'll say net is equal to neat.nn for neural network dot feed forward network dot create genome config. Okay. And now that we have the network, let's use it inside of here. So we're moving the left paddle. Let's just have the AI move the right paddle. And then that's really all we need here. I mean, we could implement some way to end the game, but I'm not even really going to do that in the test AI, because if you want to end the game, you can just click the X button, right? And here, rather than drawing the number of hits, we'll draw the score, and then we'll actually see how the AI is playing against the human. And you'll notice that the AI will be unbeatable based on the way that I've coded this Pong game out. So let's go here and let's now move the paddle. So really what I can do is simply copy output 2 in decision 2 here and just paste that right here. Now we can just make this output rather than, decision, and change a few of these values here, and net2 will just be net, but this will be right paddle. And I think that will be good. Yeah, that's really all we need. And I mean, I could get rid of this if decision equals 0 pass. I'm just putting it there so it's explicit and we know that 0 means that we're staying still. So now that we've done that, we now actually have something that will test the, what do you call it here? Sorry, that will test the AI for us. What I want to do instead of drawing the score, instead of drawing the hits though, is I want to draw the score. So I'm going to say true, false. So this means we're going to draw the score, not draw the hits. And that's what we want when we're actually testing the AI out. Okay, so I think that's good for test AI. We have train AI. Now what we really need is some way to save this best AI. Now, we're not going to get this best AI for a while. We need to get to a score of 400, right? Or 50 generations. And obviously, I'm not going to sit here and just, wait for all of this to finish before recording the rest of the video. So we'll let it run. But what I will do is show you that we can use a module called pickle to actually save the object, right? To save this neural network. And then we can load that neural network in. So rather than having to retrain this every time, we just load the neural network that's really good at doing what it does, use the neural network, and then we're good to go. So I'm going to say import pickle here. Okay. This is built into Python, so you don't need to install this. And we're just going to go down to right where the winner is. And I'm going to say with open, and I'm going to say best.pickle. And I'm going to open this in WB mode, which stands for write bytes. I'm going to open this as F. Then I'm going to say pickle.dump, and I'm going to dump the winner into the file F. That's as easy as it is to actually save the neural network. So this gives you the best genome, not the neural network, gives you the best genome. So we're going to dump the genome into this pickled file. So what pickle allows us to do is actually save an entire Python object. So that's what we're doing here. So we'll open that. But then what I can do now is I can write another function. I can say define test AI. Okay, I can just take in my config. And then here, we'll just open the pickle file. So we'll say with open best.pickle in RB mode as F. Now we're going to say the winner is equal to pickle dot, and rather than dump, we're going to say load, and we're just going to load the file. So now that we have the winner genome, what I'll do is I will just call my game. So I'll say game is equal to Pong game, and then I will pass to this a window. So let's just copy the window that we made here. Okay, so let's paste that there. So we'll say Pong game, we'll pass window width height, and then we'll say game dot test AI, and we'll just pass the winner. And that's all we need. That will run the game for us. Now we can test the AI. So what I can do is I can just, after I run my neat algorithm, I can say test AI. I can pass my config, and then if I have the best.pickle file, so as soon as this training is done, what I'll do is I'll comment this out. And now I'll just test the AI, right? So rather than running the neat algorithm, we just test the AI, and then we'll be good to go. Okay, hopefully that makes sense. Let's go here. And okay, we just got a funny one there where they were both kind of stuck at the top of the screen, just hitting it back and forth. But we should notice there's been some pretty decent progress. Like at least when I'm looking at this right now, it looks like a lot of them are rallying. This is something that will happen. It just, it's going to happen the way that I've coded this out. It's possible for it to kind of go in that way. But since the ball comes off at a random angle, it should be rare that that's going to occur. And of course, if you're playing against the AI, then you would be able to hit the ball in a way where you kind of get it off. And so the two AIs, I guess, are just, they don't want to move and they're both staying at the bottom of the screen. Anyways, I'm not going to watch this. I have been looking at this like all day before filming this tutorial. I'm going to close this and I'm just going to change the fitness threshold to be very small. And then I'm going to take whatever the best AI is that we have and show you how we test it, even though it's not going to be as good as you can get, right? And then obviously you guys know you can just train this for longer, you'll get a better AI, and then you can test that AI. But I don't want to wait because this is going to take a really long time, right? Like the average generation time, 139 seconds. So let's close this. Now, all of our work is not lost. We still have checkpoint 7. So now what I'm going to do is restore from checkpoint 7, right? If I wanted to. Okay, so restore from checkpoint 7. And I will just, actually, we're going to have an issue here. I'll talk about what the problem's going to be in 1 second, but if we restore from checkpoint 7, we can just keep training and we'll start where we stopped off. Now, the issue here is that the configuration file, if I make a change now, after I already started training and I resume from a checkpoint, it's not going to take effect. So what I wanted to do is I wanted to just change the fitness to be like 200 or 100 and just wait until we got that, which would be a lot faster. But since it's not going to take effect, any change I make here, since we're resuming from a checkpoint, what I will do is I'll just make it so that whatever the best AI is of the next generation that we run is the one that we get. And the way I'm going to do that is I'm going to change this to just run 1 generation. So we'll resume from checkpoint 7, and then we'll resume, and then we'll run 1 generation, and whatever we get from that generation will pickle, right? And then it should test the AI. Excuse me, and my voice is starting to go here, and then we should just be able to play against it. Okay, so let's clear, and let's run. And we'll wait for the 1 generation to finish. Once that's done, I'll be right back, and then we'll see how the best AI holds up against me. All right, so I just finished running the generation, and you can see best.pickle has been saved. Now, what I've done is I've just commented out run neat, and now I have test AI. And I just made a small fix here. In game.testAI, I need to pass config as well. So winner and config. This code will all be available from the description as well, so don't worry if you're missing some of the fixes. And then inside of my test AI function here, I need to fix a few things. So wherever I have game, I just need to put self before it because when I copied this in, it wasn't in a class, so I didn't have self. And then here where I have decision, I need to change this from output to be output. And then here where I have game loop, this needs to be self, and this needs to be self as well. So really anywhere there was game, just put a self before it. And then this was a small fix, add output to it, need to be output. Anyways, let's run this now. And again, we're just going to be testing the AI. So we're just calling this function and it should open best.pickle. Now I have no idea how well the AI is going to perform because we only ran it for 7 generations. Okay, you can see, so it missed it. Looks like it's getting close. Okay, it actually hit the ball that time. And it's kind of a bit jittery, but let's see how it does. Okay, nice. So it's actually working slightly, right? Now, again, we only ran for 7 generations. It kind of glitched on that one. That was weird. It looked like it was going and then it stopped moving. But if you run this for more generations, you will get a perfect AI, and I have had many perfect AIs when I was kind of testing this beforehand. So yeah, with that said, I think I'm going to end the video here. Now, this was a lot to record. I don't know how long the video will end up being because I have to edit a ton of stuff out. But it's only almost 3 hours of me recording this. So if you guys appreciated this, please do leave a like. Subscribe to the channel. I understand it was a little bit all over the place, but something like this is difficult to film because it's hard to know when to either over-explain or under-explain something and what the general competence of the audience is going to be, because this is a complicated thing. Requires neural networks, machine learning, artificial intelligence, advanced Python code. So there's a lot that I could have explained, and I could have made this video a lot longer. Anyways, I'd love to hear your feedback on it in the comments down below. Again, please like, subscribe. I look forward to seeing you guys in another YouTube video.